Welcome, my friends! In this video, I'll be discussing section 3.6, the normal distribution, which is the most important distribution in statistics. The normal distribution looks something like this. Remember that the horizontal axis represents our quantitative variable, and the vertical axis is representing how likely the value is to occur. So this means that values that are close to the mean are the most likely. As you move to values that are either less than or greater than the mean, the further away you go from the mean, the less likely that value is to occur. Here are the characteristics of the normal distribution. The normal distribution is unimodal, meaning it has one peak, and that peak occurs at the mean and median. So that also means that the mean and median are equal in a normal distribution. The normal distribution is symmetric about the mean and is described as bell-shaped. So we kind of have a mirror image on either side of the mean, either to the left or to the right, and the shape kind of looks like a bell. The normal distribution is also asymptotic about the horizontal axis. That means that the distribution gets closer and closer and closer to the horizontal axis, but technically never hits it. So that means the further away you get from the mean, the less likely a value is to occur, but technically it never reaches zero. Most variables won't follow a perfect normal distribution, but many variables can be described as approximately normal. Here's what that might look like. This histogram does not perfectly fit the normal curve, but it can be approximated by it. So we might say that this variable follows an approximately normal distribution. Now there's something called the empirical rule, which applies specifically to normal distributions and comes in three separate statements. The first statement is that about 68% of the observations will fall within one standard deviation of the mean. So what that looks like is if we have the mean right down the middle of our normal distribution, if we either add the standard deviation or subtract the standard deviation, we will get two separate values. And 68% of the observations on that normal distribution will fall between whatever those two values are. The second statement relates to 95% of the observations, which will fall within two standard deviations of the mean. So that means if you add the standard deviation twice and subtract the standard deviation twice, you will get two different numbers. And 95% of the time, a value sampled from a normal distribution will fall between those two values. Finally, the third statement states that about 99.7% of the observations, or almost all of them, will fall within three standard deviations of the mean. So the mean plus three standard deviations, or the mean minus three standard deviations, will encompass almost all the data, or about 99.7%. Let's take a look at an example. Suppose that we have this notation, which might not be familiar to you at this point, but basically this means that we have a variable, x, which follows, that's what this little squiggly line means, a normal distribution, the capital letter N is the abbreviation for normal, with a mean of 100 and a standard deviation of 10. Let's represent this on a normal distribution. The mean 100 goes right down the middle of the distribution. Then you will want to start incrementing by the standard deviation as you go to the tick marks to the right or to the left. So 100 plus 10 is equal to 110, plus 10 again is 120, and plus 10 a third time is 130. Do the same thing going to the left. 100 minus 10 is 90, minus 10 again is 80, and minus 10 a third time is equal to 70. Once you've created your normal distribution like this, it's very easy to answer any empirical rule questions. About 68% of the observations should fall within one standard deviation of the mean. So that would be between 90 and 110. Those are one standard deviation or one 10-unit increment below the mean and above the mean. So we could expect that about 68% of the observations will fall between these two values. The second number is 95%. And according to the empirical rule, about 95% of the observations will fall within two standard deviations of the mean. So that means 2 below, 80, and 2 above, which is 120. So 95% of the values will fall between 80 and 120. Finally, the third statement relates to 99.7% of the observations. 99.7% of the observations will fall within three standard deviations of the mean. So that would be 1, 2, 3 down to 70, and 1, 2, 3 up to 130. So we can expect 99.7% of the time, or about 997 times out of 1,000, a value sampled from this distribution will be between 70 and 130. I highly recommend that you memorize these three numbers so that you're prepared to answer any empirical rule questions. Alright, here's a problem for you to try. Assume the height of an adult male follows a normal distribution with a mean of 69 inches and a standard deviation of 3 inches. Pause the video and see if you can determine what heights for adult males will fall within the middle 68, 95, and 99.7% of the distribution. Alright, assuming that you've given that a try, let's go on to our next idea, which is relating to what is called the standard normal distribution, or the Z distribution. This is a special case of a normal distribution when you have a mean of 0 and a standard deviation of 1. So what that's going to look like on our picture is we will have a Z value of 0, since on the standard normal or Z distribution we use Z rather than X. And then we're going to be incrementing by 1, since the standard deviation is 1. So we'll have Z equals 1, 2, and 3 as we go towards the right, and -1, -2, and -3 as we go towards the left. Values on the Z distribution are what we call Z-scores, and they tell us how many standard deviations away from the mean a value is on a corresponding X distribution. So let me make this clear right now. Typically, the variable that you have collected will not have a mean of 0 and standard deviation of 1. So typically, the Z-scores are not going to relate to a variable that you're actually dealing with. Typically, the Z distribution, or standard normal distribution, is used as sort of a companion distribution to kind of talk about some other variable. So let me give you an example of that. Let's say that we have a variable x, which follows a normal distribution with a mean of 50 and a standard deviation of 5. We can put these values on the normal distribution as well. So we have the x value of 50 right down the middle, and then we can increment by the standard deviation as we move towards the right or towards the left. So adding 5 3 times, we have 55, 60, and 65. And subtracting 5 3 times, we have 45, 40, and 35. Now, each of these values can be thought of as corresponding to a value on the Z distribution. So for example, the x value of 55 corresponds to a Z value of 1. Or we might say that the value of 55 has a Z-score of 1. And really all that means is that 55 is one standard deviation above the mean. Or we could look at the value of 40. 40 corresponds to a Z-score of -2, meaning that 40 is 2 standard deviations below the mean. So essentially, any value on your distribution, which we call the X values, corresponds to some Z-score. And the Z-score really just tells you how far away that value is from the mean in terms of standard deviations. Now, to differentiate between Z-scores and X values, we have another term that we use specifically for the X values, and that's what we call a raw score. So whereas the Z-scores represent the number of standard deviations you are from the mean, the raw score is really just related to your variable, whether or not it be height or weight or whatever variable you are dealing with. Let's talk a little bit more about the standard normal distribution. As we mentioned, the standard normal distribution relates to Z-scores. It is a normal distribution that has a mean of 0 and a standard deviation of 1. Observations from any normal distribution can be converted into the standard normal distribution by using the following formula. We will take the corresponding raw score, or X value, subtract the mean of the distribution, and then divide by the standard deviation. Here, this is described in words. This formula tells us to take an observed value x, called a raw score, subtract the mean, and then divide by the standard deviation. This will tell you how many standard deviations the original observation is away from the mean. Let's try it with a few values from the previous slide. For example, let's take the value of 55. We know the value of 55 should have a Z-score of 1, but that formula tells us to take the X value, which is 55, subtract the mean, which is 50, and then divide by the standard deviation, which in this case you may remember is 5. And you will see that we have now converted from that X value, or raw score, into a Z-score. But the convenient thing about this formula is it will work for any value. So I don't just have to use a value that's exactly some whole number of standard deviations away from the mean. I could use, for example, let's say 62.5. So I could take 62.5 and subtract the mean of 50 and divide by the standard deviation, which is 5. And that will tell me that 62.5 is 2.5 standard deviations above the mean. So in general, the Z-score formula can always be used to convert from a raw score into a Z-score. Let's look at an example. Suppose the weight of a full-grown cat follows a normal distribution with a mean of 10 and a standard deviation of 2.5. In other words, we can write this in this way. X follows a normal distribution with a mean of 10 and a standard deviation of 2.5. Your cat, Garfield, weighs 18 pounds, and you think he's a little bit overweight, but you're not sure by how much. So here is Garfield. Maybe you've met him. And so let's go ahead and find Garfield's z-score. So to find the z-score, we can use the z-score formula. The z-score formula says to take our raw score, or in this case, the weight of our cat, subtract the mean weight of all cats, and then divide by the standard deviation. We have 18, which is the weight of Garfield. We subtract the mean, which is 10, and divide by the standard deviation of 2.5. 8 divided by 2.5 is equal to 3.2. What does this number mean? Well, remember that z-scores represent the number of standard deviations a value is from the mean. So this tells us that Garfield's weight puts him 3.2 standard deviations above the mean, quite a bit heavier than your average cat. Let's take a look at what this might look like on the standard normal distribution. We know that Garfield has a z-score of 3.2, so that puts him over here in the tail with a z-score of 3.2. Garfield's z-score tells us he is 3.2 standard deviations above the mean, quite a bit heavier than most cats. We know, based on the empirical rule, that 99.7% of the observations should really fall between a z-score of -3 and +3. So this tells us that Garfield really is in the tail here, and should probably be, laying off the lasagna. All right, we can also go backwards. So we can take a z-score and calculate a raw score. So if we take the z-score formula and we algebraically manipulate it so that we solve for x, you would get x is equal to z times sigma plus mu. And this is what we call the raw score formula. This formula could take the number of standard deviations some value is from the mean and convert it back into a value in terms of your distribution, such as the weight of a cat. So let's look at an example. Let's use this formula to find a raw score x given a z-score. If our variable x represents the weight of a cat in pounds, and x follows a normal distribution with a mean of 10 and standard deviation of 2.5, and we have another cat here, his name is Tom, and in this case, this cat is weighing 1.2 standard deviations below the mean. So we don't know the weight, but we just know how many standard deviations we are below the mean. Well, that's really just telling us the z-score. They're telling us that we are 1.2 standard deviations below the mean, or that we have a z-score of -1.2. So using the formula, we can take the z-score of -1.2, multiply by the standard deviation, which is 2.5, and then add the mean, and the result will be 7. So that tells us that Tom must weigh 7 pounds. So here's what that's going to look like on the standard normal distribution. We have Garfield all the way over here with a z-score of 3.2 and an x value of 18, and then we have Tom, which this is Tom from Tom and Jerry, and he has a z-score of -1.2, putting him a little bit below the mean, which corresponds to a weight of 7 pounds. So whereas Garfield was really an outlier in terms of the weight of a cat, Tom is a little bit more typical, or a little bit below average. All right, here is a problem for you to try. Test scores in a class follow a normal distribution with a mean of 80 and a standard deviation of 7. In other words, our variable follows a normal distribution, mu equals 80, and sigma equals 7. So here are a few questions for you to try. See if you can determine if a student scored an 89 on the test, how many standard deviations is that student from the mean, and also if a student scored 2.4 standard deviations below the mean, what is that student's test score? And you can solve these by using these two formulas here. So go ahead and pause the video and give that a shot. And that is all I have to talk about in this video, so I will see you in the next one.